Hello, I'm Jacob Helms, and I was the geotechnical lead for this project.
Hello, my name is Lucas Brockman, and I was the structural lead for this project.
I am Melissa Hancock, and I am in charge of the transportation and sustainable solutions.
Hi, my name is Blake Burkhart. I'm in charge of the hydrologic design.
Hi, my name is George Zambrano, and I'm the transportation engineer for this project.
Hi, my name is Dawson Klingler, and I was the structural lead for this project. JDJMLB Engineering was approached by Dr. Nick Hudema, representing a local company, to perform a site layout and design of a commercial facility in Nampa, Idaho. Here we can see the building footprint overlaid onto the topographic map of the 1-acre site. The site itself consists of a river that lies to the west, and the base flood elevation is 2,507 feet. The project required designs from 4 components of civil engineering: geotechnical, hydrologic, structural, and transportation. Specialists from these fields were required to collaborate and produce a final design and site layout. The deliverables for this design included a structurally engineered 2-story building supported by a geotechnically designed foundation, traffic flow optimized for safety, asphalt designed to withstand various loadings, and a stormwater retention facility designed to capture excess surface water runoff. Sustainable and green solutions were also incorporated into this design at the request of the owner. My team members will showcase each of the design elements for the remainder of this presentation.
The geotechnical aspects of this project included 5 areas: a subsurface investigation, a foundation design, settlement and earthwork calculations, then a site grading plan. The subsurface investigation would be performed by requesting borings across the site to determine the stratigraphy of the site, then the properties of the native soil. Using the subsurface investigation information, we would then design the foundation. This includes footing size, shape, and depth, as well as fill considerations. Settlement would be calculated based on the footing size and loading information. This is then compared to acceptable values, which will inform further foundation design. Earthwork calculations will take place throughout the process to monitor the amount of cut and fill. The site grading plan will detail the end topography of the site. We had a limit to the number of bores that we were allowed to request. We set a limit to ourselves to keep the number of bores less than 8, and we provided a limit that only 2 could be requested within the building footprint. Originally, the foundation was focused on being the most economic option. This was changed in favor of having a safer design. Based on the locations of the isolated columns, we had to limit the size of our foundations so that there would be no overlapping of the foundations. Settlement didn't have a set limit, but our group operated on the work done by Skempton and McDonald in 1956, which proposed a limit of 1.26 inches for a building built on sand. Earthwork, as well as the site grading plan, was to be limited for both cost and sustainability purposes. Limiting the amount of cut, fill, and general traffic related to bringing fill in and out of the site would be both helpful to costs and the surrounding environment. The City of Nampa Design Code also requires a 5% slope for 10 feet around the foundation of the building. Geotechnical design also collaborated with the hydrological design to utilize the site's natural topography to direct runoff into the proposed location of the retention pond. The subsurface investigation was conducted using 6 bores, 2 being within the footprint of the building, 3 along the roadway, and 1 within the retention pond. These were spaced in such a way that the stratigraphy of the site could be generalized accurately. With the 6 bores, we found that the site had a top layer of very dense silt with a depth that increased from 6 foot to 10 feet going east to west. Beneath this layer was a layer of dense silty sand. We determined that the silt would not be an ideal material to build on, so structural fill would be used in its place. To limit differential settlement, we would excavate until 8 feet below the footprint to remove all silt within the area of the building and replace with a structural fill. Using a factor of safety of 3.5 and a depth of 4 feet for the continuous footings and the isolated footings, we found that the isolated footings would have a 3.5 by 3.5 foot square design, and the continuous footings would have a width of 5 feet after rounding up to the nearest half foot. Typical estimates and designs with these particular dimensions had a thickness of 1 foot for both. Using the column loads and the density of the fill, we determined that the settlement as a result of the underlying sand layer would only be 0.31 inches, which is well less than the requirement set by Skempton McDonald of 1.26 inches. The amount of earthwork that was required included only the structural fill operation described earlier. With a surface area of roughly 7,900 square feet, the amount of cut and fill totaled 63,200 cubic feet. Operating off an assumed density of 114 pounds per cubic foot for the structural fill, this would mean a total of 3,600 tons of structural fill required. The site grading plan was able to be limited to the minimum set by the City of Nampa Design Code. A 5% grade for 10 feet would allow the perimeter would follow the perimeter of the building. The natural topography of the site would then move water downhill to the retention pond.
There are two main sources of design criteria for the stormwater management portion of this project. First, the client had a few requirements for their future manufacturing facility. The client had stated that they required a stormwater retention facility, also known as a retention pond. Basically, all stormwater that falls onto non-natural surfaces, such as the roof of a building or roadway, must be deposited into the ground for groundwater recharge. Retention ponds differ from detention facilities, in which detention facilities manage stormwater by flowing into nearby surface sources. The client had also mentioned that all stormwater runoff must be contained. If the stormwater is allowed to breach the pond area, it could enter the city storm drain system and possibly pollute local waterways. Given site data also included that the groundwater table is consistently 12 feet below the ground surface. The NAMPA Engineering Development Process and Policy Manual was the main source of design criteria for this project. The design manual included the intensity, duration, frequency curves that statistically determine the overall rainfall depth for a 100-year storm in Nampa, Idaho. The minimum side slope steepness of 3 rise to 1 run is required to prevent scouring or collapse of the pond sidewalls. A 3-foot maximum standing water depth is necessary for personal safety issues. For acceptable filtration before entering the groundwater, stormwater runoff must be passed through a 3-foot layer of fine-grained porous medium. While water quality is not a design requirement for this project, meaning a sand and grease trap layer was not necessary, this design criteria is still important as a minimum expectation for water quality. The NAMPA design manual states that no standing water should exist 24 hours after the storm event has ended. This means that the water must percolate into groundwater or evaporate within 24 hours. This is beneficial to insect management, which is another safety concern. Lastly, standing water must remain 1 foot below any building entrances. It is important that no water damage occurs to the manufacturing facility, especially the building itself. So with this criteria in mind, a dry well pond hybrid was created. This slide features a cross-sectional view of the design, detailing the height and width of several layers necessary to fulfill all the requirements. The design length is 66 feet, and the pond lies parallel to the western boundary of the site. At approximately 10.5 feet below the ground surface lies a deep layer of silty sand with an estimated infiltration capacity of 4 inches per hour. In order to utilize the native soil's relatively high drainage rate, the sandy silt topsoil must be removed. A 1.5 foot layer of imported sand is then imported so that the stormwater is sufficiently clarified. In order to maximize the volume of this deep trench that was dug, a 5-foot layer of poorly graded 3/4 inch clean crushed stone was added atop the filtration layer. This layer has a high percentage of void spaces so that during a rain event, the effective depth is much greater than a traditional pond, while still fulfilling the design criteria of having the maximum standing water depth be 3 feet. In an event of a 100-year storm, stormwater will be directed to the retention facility via roadside gutters. The rainfall will fill up the pond to 1 foot below the ground surface, while the pond transfers the stormwater back into groundwater during and after the storm. The storm is successfully managed with this design. Primary catchment systems such as gutters were not design requirements. However, the site was graded with a drainage gradient of 1% in the east-west direction to ensure that the runoff will make it to the retention pond without the water ponding on any side, on any surface.
For the structural design, there were several things that needed to be designed for this building. The roof system that had to include a flat deck and joist that had to accommodate the anticipated loadings in Nampa, Idaho, and fit all design criteria, as well as elevators floors. They had to be designed as one-way slabs, and supporting elements such as beams and columns also had to fit within code regulations and the demand loads of the building. The elevated surfaces, there were 2 things that were designed for. The deck type, which was a 1.5 B20 deck with triple spans, and then the joist types. We had 3 different joist types. We had a 30K9 joist types at 43 feet at 9-foot spacing, a 30K10 at 47-foot spans with 9-foot spacing, and an 18K3 at 23-foot spans with 9-foot spacing. We also had a W3 Formlock 18-gauge triple span with 9-foot spans for our floor type for the elevated floors. For the beams, we decided to go with steel beams, and we have W16 by 100, 43-foot beams, and we have W10 by 54 with 7-foot span steel beams. For the columns, we all decided to do one column type. They would be 12 by 12 inch reinforced concrete square columns. And with the reinforcing steel, they would have 8 number 8 bars in longitudinal steel and number 3 stirrups at 12-inch on center spacing.
There were 3 general design requirements for this transportation project: entrance and exits, vehicle and pedestrian flow, and pavement design. The driveway was modeled after Standard Drawing 807 from the 2015 edition of ISPWC, Typical Commercial Driveway Approach. The standard drawings indicate a 90-foot taper section before the beginning of the curb radius. Due to the nature of the site, the taper section and curb radius are limited to 27 feet from the edge of the property to the edge of pavement. To ensure that the driver can safely access the site, an exaggerated taper was created. Safety was a top priority when designing the exits for the site. Both the entrance and exits are delineated with clear and visible bright yellow pedestrian walk paths. To facilitate the flow of traffic within the site, a one-way system was employed. This was to create a predictable traffic pattern, both for drivers and pedestrians alike. The one-way system creates an entrance driveway and an exit driveway. The entrances and exits are clearly labeled. One-way signs are used throughout the sites, and do not enter or wrong way signs are also employed. An added benefit to the one-way system is that it simplifies the pavement design. From the entrance, we have unloaded trucks coming in, and in the exit, we have loaded trucks going out. A 10-mile-an-hour speed limit will also be observed within the site to give drivers the maneuverability that is required within the site. Table C2 summarizes the minimum 180-degree turning capabilities of the SU-25 and assumes a maximum steering angle of 31.8 degrees. The maximum steering angle assumed for this diagram is not the true maximum steering angle of an SU-25 truck. For example, the Kenworth T800, which we used in our model, has a maximum steering angle of 54 degrees. While our site does require the driver to perform a 180-degree turn, it is not what we would describe as a U-turn per se, where it's done in one fell swoop. The 10-mile-an-hour speed limit allows for much greater maneuverability, and also the attack angle at which the driver takes the corner can be varied as well to avoid any potential obstacles. The pavement design for the site was created using the Idaho R-value method. With reasonable assumptions and a lot of trial and error, an appropriate pavement design was chosen. While there were many values to solve for and derive in this process, it was the equivalent single axle loads that were most pivotal. It takes into account the nature of the site, like how many days a year it's open, for how long are we designing this to last for, and then also the weight and frequency of the trucks that are going to drive on this road. Equivalent single axle loads, or ESALs, are very dependent on load equivalency factors. Charts for load equivalency factors exist, but as can be seen from the diagrams below, it is highly dependent on your structural number, your terminal serviceability index, and then also the number of axles. Terminal serviceability index is generally a designer choice, a value of 3 reserved for freeway or interstate use, but generally a value of 2 or 2.5 is used. For the pavement design shown in the picture, which is the entrance to the site, a terminal serviceability index of 2 was chosen. The total ESALs were calculated with a 20-year design life in mind. The frequency of trucks was assumed to be 15 trucks per day, which is greater than the anticipated 12 trucks per day. This method was first solved on pen and paper to figure out the logistical efforts that would be required. After that was solved, I was able to create an Excel that incorporated all the different serviceability indexes, structural numbers, and any other assumptions that need to be accounted for. The final pavement design for the entrance portion of the site closely resembles that of collector and local roads within the county. 3 inches of pavement, 6 of base, and 15 of subbase. For our site, we added an additional 1.5 inches of a top layer for water protection, as well as nice aesthetics.
Sustainability is one of our core values when it comes to project designs. Based off of research and previous projects completed, we were able to compile various green and sustainable solutions to include in our design. One of the biggest solutions includes the use of sustainable materials such as structural steel and compressed earth blocks, which are an alternative to cement blocks. Reducing the amount of materials needed for the design is another way we have been able to reduce our carbon footprint. Instead of paving the entire area cars and trucks will be driving on, we decided to go with a gravel parking lot to help relieve the amount of asphalt we will be requiring. The only paved part of the parking lot will be the accessible parking spot. In addition, we have created a pavement design that involves a gradual increase of thickness as the different weights of trucks will be going around the building. The heaviest weight limit is located from the hopper onto the main road. On a similar note, we have created a foundation design that minimizes the amount of excavation and fill needed for the project. The plot of land itself actually has a natural downgrade toward the water retention pond, so this helped to our advantage. This not only reduces the amount of material needed, but also the amount of manpower required to get the job done. Moving on, we are including a green roof along with solar panels and skylights. Green roofs provide many benefits, including cleaner air, reduction of the building's energy usage, support to wildlife, and reducing the amount of stormwater runoff. Finally, the water retention pond has design aspects to create a more sustainable surrounding environment. Different plants will line the outside of the pond to create a natural filtration system for the runoff to flow through before entering the pond. This will result in cleaner water sitting in the pond before returning back into the environment. While this is not a traditional aspect of typical civil design, aesthetics were considered and incorporated within the design of the industrial site. For the most part, landscaping will account for the majority of the aesthetics to the project design. Trees, plants, and flowers will be planted on the site as well as placed on the roof. And with that, this concludes our project design. Thank you for watching.